You experience time every moment of your existence. Right now, as you watch this, time is moving forward. Your heart is beating. Your neurons are firing. Memories are forming. The future is becoming the past. You believe time is real because you feel it passing. But what if everything you believe about time is fundamentally mistaken? What if time is not a flowing river, but a landscape, static, unchanging, eternally present? What if the past and future exist right now, simultaneously, and the sensation of the present moment is an illusion created by your consciousness? Over the next hour, we will explore one of the deepest mysteries in physics and philosophy. Is time actually real? Not metaphorically, not philosophically, but physically real? And the answer may overturn everything you believe about existence itself. Right now, in this moment, you are alive. You are conscious. You are aware of the present instant. This moment feels real. It feels substantial. It is the only moment that truly exists from your perspective. The past is gone, reduced to memory, to traces, to history books. The future has not yet arrived. It exists only in imagination and anticipation. The present moment is the only time that feels genuinely real, genuinely now. Yet this intuition, this felt sense of the present moment, may be one of the most profound illusions consciousness creates. Consider what we mean by now. The present moment is supposed to be the boundary between past and future. But what is the duration of the present? Is it 1 second, 1 millisecond, 1 nanosecond, 1 Planck time unit, the smallest meaningful interval of time in physics, approximately 10 to the minus 43 seconds? The moment you specify a duration, you divide that duration into smaller pieces. Half a second is not the present. Only an infinitesimal instant at the boundary can truly be now. But an infinitesimal instant has no duration. It cannot contain any events, any experience, any change. An infinitesimal present moment is almost like not existing at all. Philosophers have pondered this paradox for millennia. Augustine of Hippo, writing in the 4th century, expressed confusion about the nature of time. What then is time? If no one asks me, I know. If I wish to explain it to one that asks, I know not. The problem Augustine identified remains as acute today as it was 16 centuries ago. From moment to moment, the world changes. Objects move, light travels, hearts beat. Consciousness flows from one thought to the next. Yet in each infinitesimal present moment, nothing changes. Change requires time. It requires a before and an after. But the present, the true present, the infinitesimal boundary between past and future, contains no time. It is a knife edge between two eternities. This is the paradox of the present. It feels real to us, yet the more carefully we examine it, the more it dissolves under scrutiny. The present moment seems to be the most fundamental aspect of reality, the ground of all existence. Yet it may be the most illusory. Physics offers no privileged present moment. In Einstein's theory of relativity, time is woven together with space into a 4-dimensional fabric called spacetime. The past, present, and future all exist in this fabric simultaneously. They are not separated by the passage of time, but are arranged along the temporal dimension like pages in a book, all present at once. From this perspective, the present moment is not a real feature of the universe, but merely a particular slice through space-time, a slice that depends on the observer's reference frame. Different observers, moving at different velocities, will disagree about which events are simultaneous, which are past, which are future. There is no objective now that all observers agree upon. The present moment is relative, subjective, observer-dependent. It is not a fundamental feature of reality, but a perspectival artifact of consciousness. Yet our conscious experience insists otherwise. We feel the present moment flowing into the future. We feel time passing. We remember the past and anticipate the future, but we are always irreducibly in the present. This gap between the physics of time and the phenomenology of time, between what we measure and what we experience, is one of the most profound mysteries in science and philosophy. Is the present moment real or illusory? Does time truly flow, or does the sensation of flow emerge from the structure of consciousness, observing an unchanging, eternal space-time? These questions are not mere academic puzzles. They touch on the fundamental nature of existence, causality, free will, and the meaning of a human experience. For most of the human history, time was understood as a fundamental, irreducible aspect of reality. Time was the medium in which events occurred. Events happened in space at particular locations and at particular times. Space and time were distinct categories. Space was where things existed. Time was when they existed. This was the Newtonian picture of the universe, based on Isaac Newton's revolutionary framework of classical mechanics developed in the 17th century. In the Newtonian picture, time flows at the same rate everywhere. An instant on Earth is the same instant on the Moon or on distant stars. Time is universal, absolute, independent of anything else. Space could be curved or warped by the presence of massive objects, but time was not affected. Time simply marched forward at a constant pace. The same for all observers, everywhere in the universe. This picture was elegant and intuitive, and it worked remarkably well. Newtonian mechanics could explain planetary motion, projectile trajectories, and countless other phenomena. It accurately predicted eclipses centuries in advance. It provided a framework so powerful and so successful that it seemed time's nature must indeed be as Newton described. Then in 1905, a young patent clerk in Bern, Switzerland, named Albert Einstein, published a paper titled "On the Electrodynamics of Moving Bodies." This paper introduced the special theory of relativity, and it shattered the Newtonian picture of time. Einstein began with a simple observation: the laws of physics are the same in all inertial reference frames. All frames of reference moving at constant velocity relative to each other. This principle seems intuitive enough. But Einstein combined this principle with a second, more startling assumption. The speed of light in vacuum is the same for all observers, regardless of their motion. This seems impossible at first. If you are moving forward at 100 km per hour and throw a ball forward at 50 km per hour, a stationary observer sees the ball moving at 150 km per hour. Speed should be relative to the observer's motion. Yet Einstein proposed that light is different. Light always travels at approximately 300,000 km per second, regardless of the observer's motion. If you move toward a light source at enormous velocity, light still approaches you at the same 300,000 km per second, not at a faster speed. This assumption leads to strange consequences. Time is not absolute. The passage of time depends on the observer's velocity and gravitational environment. A moving clock runs slower than a stationary clock. A clock in a stronger gravitational field runs slower than a clock in a weaker field. The faster an object moves, the more time slows down for that object, relative to stationary observers. At the speed of light, time effectively stops. This phenomenon is called time dilation, and it is not a theoretical curiosity. It has been experimentally verified countless times. Muons are particles created when cosmic rays strike the upper atmosphere. They decay rapidly. Their average lifespan is about 2.2 microseconds. At this rate, muons created in the upper atmosphere should decay before reaching the Earth's surface, located 10 kilometers below. Yet muons do reach the surface in measurable numbers. Why? Because the muons are moving at nearly the speed of light. Time slows down for them relative to stationary observers on Earth. From the muon's perspective, the journey takes much less time than it would if time flowed at the normal rate. The muons decay more slowly relative to Earth clocks and manage to reach the surface before decaying. This is not metaphor or mathematical abstraction, it is physically real. Astronauts who spend time in orbit age slightly less than people on Earth by microseconds, but measurably so. This effect, called gravitational time dilation, depends on the strength of gravity and the proximity to massive objects. Astronauts at the altitude of the International Space Station age about 0.0007 seconds less per 6-month mission compared to people on Earth's surface. In 1915, Einstein published his general theory of relativity, extending these ideas to include gravity. In general relativity, space-time is not a static, fixed background, it's dynamic. The presence of mass and energy warps and curves space-time. This curvature is what we experience as gravity. A massive object like the Earth curves the space-time around it, and other objects follow the paths through this curved space-time. What Newton called the gravitational force is actually the geometry of space-time itself. Crucially, general relativity treats time as part of space-time. Time is not separate from space, but intertwined with it into a 4-dimensional continuum. In this framework, time is not a flowing river, it is a dimension, like the spatial dimensions. The past, present, and future are arranged along this temporal dimension like pages in a book. They all exist simultaneously in space-time. This leads to a radically different picture of time's nature. In the Newtonian picture, time flowed from the past through the present into the future. The present moment was the only moment that existed. The past was gone, the future was not yet. But in Einstein's picture, all moments exist simultaneously in space-time. The distinction between past, present, and future is not a fundamental feature of reality, but depends on the observer's reference frame. Two events that one observer considers simultaneous, happening at the same time, may be separated in time for another observer moving at a different velocity. There is no privileged reference frame, no absolute now that all observers agree upon. The present moment, the boundary between past and future, is not an objective feature of the universe, but a subjective, observer-dependent slice. Through space-time, the implications are profound. If all moments exist simultaneously in space-time, then time is not flowing. The sensation of time flowing, the feeling that the future is coming into being and the past is receding into memory, may be an illusion created by consciousness. The universe is not dynamic and becoming, it is static and complete. Hermann Minkowski, a mathematician who developed the mathematical framework of space-time, expressed this idea most starkly in a famous statement made in 1908. Henceforth, space by itself and time by itself are doomed to fade away into the mere shadows, and only a kind of union of the two will preserve an independent reality. In other words, space and time are not fundamental. Only space-time, the 4-dimensional union of space and time, is real. This is the block universe picture, also called eternalism. The entire history of the universe, all events from the Big Bang to the distant future, exists simultaneously in space-time. There is no privileged present moment. The sensation that the present is special, that now is real while the past is gone and the future is not yet born, is an artifact of consciousness, not a feature of physical reality. Yet if all moments exist simultaneously, in space-time, why do we experience time as flowing in only one direction? Why can we remember the past but not the future? Why does an egg break into pieces, but pieces never spontaneously assemble into an egg? Why does disorder always increase? The answer lies in thermodynamics, the study of heat and energy transfer. The second law of thermodynamics states that the entropy of an isolated system always increases, or stays the same. It never decreases. Entropy is a measure of disorder. In a closed system, disorder tends to increase. A broken egg does not spontaneously reassemble. A hot cup of coffee left on a table cools down. It never spontaneously heats up. A diffuse cloud of gas never spontaneously concentrates into a denser cloud. Disorder increases, order decreases. This law is not a prescription or a guideline. It is a fundamental principle grounded in probability and statistics. In the atomic realm, particles move randomly. When you heat one side of a room, the heat spreads throughout the room over time. This is not because heat is attracted to cold regions, but because there are far more configurations of atoms where heat is evenly distributed than configurations where all heat remains in one corner. Statistically, the randomly moving particles will eventually arrive at the most probable configuration: maximum entropy, perfect disorder. Herein lies the arrow of time. The direction of increasing entropy defines the future. The past is the direction of decreasing entropy. This is called the thermodynamic arrow of time. The universe was born in an extraordinarily ordered state, the Big Bang. All energy and matter was concentrated in an infinitely small, infinitely hot point. This was a state of extremely low entropy. Since then, the universe has been expanding and cooling. Entropy has been increasing. Stars have formed and eventually will burn out. Galaxies will collide and merge. Matter will decay. Black holes will evaporate. Eventually, the universe will reach a state of maximum entropy, heat death, a state in which energy is uniformly distributed throughout an infinitely large, infinitely cold cosmos. At that point, entropy cannot increase further. The thermodynamic arrow of time points from the low entropy past toward the high entropy future. We remember the past and not the future because memory formation requires increasing entropy. The act of encoding a memory into physical form increases disorder in the brain. The brain can only form memories of events that have already increased entropy, that is, of the past. Creating memories of the future would require entropy to decrease, which violates the second law of thermodynamics. This is a profound insight. The direction we experience time as flowing is directly connected to entropy increase. We experience time as moving forward because entropy is increasing. If entropy were decreasing, our experience of time's direction would reverse, yet this raises a ameonelo mystery. Why was the early universe in such a low entropy state? Why did the Big Bang produce such an ordered configuration? In the Newtonian picture, this was simply a fact to be accepted. The universe began in a particular state. Why ask why? But in the context of Einstein's spacetime picture, where all moments exist simultaneously, this question becomes more pressing. If the past and future are equally real, equally existent in spacetime, why does one direction, the future, have higher entropy than the other, the past? This is called the problem of the arrow of time. Physics treats past and future symmetrically. The fundamental laws of physics are time symmetric. They work backward as well as forward, yet we observe a clear asymmetry. Entropy increases in one direction only. Why? Some physicists and philosophers have proposed solutions. One possibility is that the universe undergoes cycles: expansion followed by contraction, heat death followed by rebirth. Each cycle begins with a low entropy state and progresses to high entropy. In this cyclic picture, the past is defined as the direction of increasing entropy from one Big Bang to the next. The low entropy condition is not explained by appeal to chance or accident, but is built into the structure of the universe itself. Another possibility involves quantum mechanics and the role of observation. Some interpretations of quantum mechanics suggest that the act of observation affects reality. When we observe an event in the past, we are observing information that has reached us through light and other signals. The creation of these signals increased entropy. From this perspective, the asymmetry between past and future is fundamentally connected to the nature of observation and measurement. The past is what can be known through observation. The future is what cannot. This asymmetry is a feature of consciousness and observation, not of physical reality itself. Yet another approach, called the Boltzmann brain hypothesis, suggests that consciousness itself may be rare and improbable. In an infinite universe, spontaneous fluctuations can create conscious observers out of random configurations of atoms. These observers experience the thermodynamic arrow of time because they can only exist and have memories in regions of spacetime where entropy has recently increased. This selection effect, We can only observe time flowing in the direction of increasing entropy, because observers can only exist in such directions. May explain the apparent asymmetry. All of these solutions remain controversial. The problem of the arrow of time remains one of the deepest unsolved mysteries in physics. In 1905, when Einstein published his theory of special relativity, he introduced a discovery that challenged our most basic intuitions about time. The relativity of simultaneity states that two events that are simultaneous for one observer may not be simultaneous for another observer, moving at a different velocity. This can be illustrated through a famous thought experiment. Imagine a train moving at enormous velocity relative to the ground. Lightning strikes both the front and back of the train simultaneously in the ground observer's reference frame. The light from both lightning strikes travels toward an observer standing in the middle of the train. From the perspective of the ground observer, the two lightning strikes are simultaneous. They happen at the same instant. The light from both reaches the middle point of the train at the same time. But from the perspective of the observer on the train, the situation is different. The observer is moving toward the lightning strike at the front of the train and away from the lightning strike at the back. Light from the front strike, the one the train is moving toward, reaches the observer sooner than light from the back strike. From the train observer's perspective, the front strike happens before the back strike. The two events are not simultaneous. This is not a matter of perception or timing of the signals. This is a fundamental feature of spacetime itself. The simultaneity of events depends on the observer's motion. There is no absolute objective now that all observers agree upon. What is past for one observer can be present or future for another, depending on their velocity. This has profound implications. It means that the concept of a global present moment, a slice of spacetime that is now for the entire universe, is not a feature of physical reality. It is observer-dependent, subjective, relative. Consider two distant galaxies separated by billions of light years. In your reference frame, you might conclude that a particular event in galaxy A is simultaneous with a particular event in galaxy B, but an observer moving at a different velocity would disagree. They would conclude that the events are separated in time. There is no objective truth about whether the events are simultaneous. The truth depends on who is observing. This destroys the idea of absolute time. It destroys the notion that there is a real, physical present moment sweeping across the universe. Instead, we must accept that simultaneity is relative, observer-dependent, and there are many equally valid ways of slicing spacetime into past and future. The physicist Hermann Minkowski developed a mathematical representation of this called a light cone. For any event, one can ask, which other events can possibly be connected causally to this event? Which events could possibly influence it or be influenced by it? An event at a particular location and time divides spacetime into regions. The future light cone consists of all events that could possibly be influenced by the given event. These are events that lie in the future and are close enough that a light signal from the given event could reach them. The past light cone consists of all events that could possibly have influenced the given event. These are events in the past close enough that a light signal from them could reach the given event. Between the future and past light cones lies what physicists call elsewhere, a region of space-time that is neither in the future nor the past light cone. Events in elsewhere cannot causally influence the given event or be influenced by it. Yet whether an event lies in the future, past, or elsewhere depends on the observer's reference frame. What is elsewhere for one observer lies in the future for another. This completely dissolves the notion of a global present moment. Different observers will disagree about which events are happening now, and all observers are equally correct within their own reference frame. There is no universal now. Yet in our daily experience, we do experience a present moment. We do seem to experience events in a sequence. We remember the past and anticipate the future. How can this be reconciled with Einstein's relativity? One solution is the moving spotlight theory. In this view, the present moment, the now, is real, but it is not a global, universal feature of spacetime. Instead, it is a local property that depends on the observer. Different observers have different moving spotlights. Your spotlight illuminates one slice of space-time as now. A distant observer's spotlight illuminates a different slice. All these observers are seeing different moments as present, and all are correct within their reference frames. But even this requires accepting that time is not globally flowing. Time is not moving forward for the entire universe at once. Each observer experiences time flowing in their own reference frame, but there is no objective fact about which moment is now for the universe as a whole. In the early 20th century, as Einstein was developing relativity, another revolution was quietly building in physics: the quantum revolution. The study of atoms and subatomic particles revealed that at tiny scales, reality behaves in ways radically different from our macroscopic experience. In quantum mechanics, particles do not have definite positions or velocities until they are measured. Instead, they exist in a superposition of all possible states. An electron in an atom does not orbit the nucleus like a planet around a star. Instead, it exists in a cloud of probability, a wave function that describes all possible locations where the electron might be found if measured. This uncertainty extends to time as well. At the Planck scale, the extremely small scale of 10 to the minus 43 meters, space-time itself becomes uncertain and foamy. Quantum fluctuations create and destroy virtual particles. The structure of space-time at this scale is not smooth, but grainy and probabilistic. Some physicists have proposed that at the Planck scale, time itself becomes uncertain. The Planck time is approximately 10 to the minus 43 seconds. At shorter timescales, the concept of time itself may break down. We may not be able to meaningfully speak of events separated by less than a Planck time. This raises a profound question. If time is uncertain and foamy at the Planck scale, is time fundamental or emergent? Is time a basic feature of reality, or does it emerge from some deeper quantum substrate? Some approaches to quantum gravity, such as loop quantum gravity, suggest that space-time itself is quantized. Space and time are not continuous, but are made up of discrete, indivisible units. These units are similar to pixels in a digital image. At macroscopic scales, these pixels are too small to notice, and space-time appears smooth and continuous. But at the Planck scale, the discrete structure becomes apparent. If space-time is quantized, then time is not infinitely divisible. You cannot ask what happened in a time interval smaller than 1 Planck time. The question itself becomes meaningless, like asking what is north of the North Pole. Furthermore, in some formulations of quantum gravity, time may not exist at all at the fundamental level. The Wheeler-DeWitt equation, a fundamental equation in quantum cosmology, describes the state of the entire universe. Remarkably, this equation contains no time variable. The universe is described by a wave function that is time independent. Time appears to be absent at the most fundamental level of physics. How does time emerge if it is absent at the fundamental level? One possibility is that time is an emergent property, a feature that appears when we observe the universe at macroscopic scales, but that does not exist at the quantum level. From this perspective, time is not fundamental, but derived. It emerges from the underlying quantum structure. This is a revolutionary idea. It suggests that time, the most basic, obvious, and seemingly fundamental aspect of our experience, may not be real at the deepest level. It may be an illusion created by the way large systems of matter and energy interact and evolve. The implications are staggering. If time is emergent, then the flowing sensation of time, the arrow of time, the distinction between past and future, all of these may be features of our particular universe at our particular scale, but not universal features of reality. Some physicists, such as Carlo Rovelli, have argued for a timeless formulation of physics, in which time does not appear at the fundamental level. In Rovelli's view, the fundamental laws of physics describe relationships between physical systems, not change over time. Time is a human construct, a way of organizing our observations of these relationships. The universe itself is timeless, Yet this raises a profound question. If the universe is timeless at the fundamental level, how does time emerge? How do we experience flowing time if the underlying reality is static and time independent? One possibility involves decoherence and the wave function, collapse. When a quantum system interacts with a macroscopic environment, the delicate quantum superposition is destroyed. The quantum probabilities collapse into classical certainty. The measurement process introduces an arrow, a direction from quantum uncertainty to classical certainty. This might be the origin of the thermodynamic arrow of time and the direction of time's flow. Another possibility involves the structure of conscious observation. Some quantum interpretations suggest that consciousness plays a role in wave function collapse. If this is true, then consciousness might be responsible for creating the direction of time and the flow of moments. We would be creating time through the act of observation. This is highly speculative and controversial, but it highlights a genuine mystery. How can a universe described by time-independent quantum mechanics give rise to the flowing directional time we experience? If time is not fundamental at the level of physics, perhaps it is created by consciousness. Perhaps time, the flowing present moment, the division of experience into past and future, is generated by the brain. Neuroscience has revealed that the brain does not process information instantaneously. Neural signals travel at finite speeds. Signals from different parts of the body arrive at the brain at different times. The brain must integrate these signals into a unified, synchronized experience of now. This integration is not automatic. It involves computation. The brain must take information arriving at different times and bind it together into a coherent perception of the present moment. Furthermore, the brain introduces latency. Neural processing takes time. By the time information reaches conscious awareness, the events that cause that information have already passed. You cannot see an object the instant light from that object hits your retina. There is a processing delay, roughly 50 to 100 milliseconds on average. By the time you become conscious of seeing an object, the light has already reached your eyes, traveled along your optic nerves, reached your visual cortex, been processed through multiple layers of neural computation, and propagated through association areas that create conscious experience. This means that the present moment, the conscious now, is not simultaneous with the physical events causing it. Your experience of now is actually experiencing events from about 50 to 100 milliseconds ago. You are constantly experiencing a reconstructed, interpreted past, not the true physical present. Yet the brain creates an illusion that you are experiencing the present. It creates a sense that all the sensory information arriving from your body and the external world is simultaneous and occurring now. This unified sense of present experience is called the specious present. William James, a pioneering psychologist, introduced this term to describe the apparent present moment of consciousness, which he recognized must have some duration, perhaps around 1 to 3 seconds, in order for consciousness to bind together information into coherent experience. The specious present is not a true present in the physical sense. It is a temporal window created by the brain through which events are experienced as simultaneous and present. Events outside this window, events that occurred more than a few seconds ago, are experienced as memory in the past. Events that will occur in the future are experienced as anticipation or imagination, not as present. This suggests that the experience of time flowing, the sense that moments are passing, that the future is becoming the present, which then becomes the past, is generated by the brain's integration of information over time. The brain creates discrete moments of experience, each lasting a few hundred milliseconds, and chains these moments together. The transition from one moment to the next creates the impression of time flowing. But this is not how time actually flows at the physical level. The brain is constructing time. It is creating the subjective sense of temporal flow out of the processing of temporal information by neural networks. Neuroscience has also revealed that the brain's sense of time can be distorted. Certain drugs, certain neurological conditions, and even intense emotional states can alter the subjective experience of time's passage. Time seems to slow down during emergencies or moments of intense fear. A fall that lasts 2 seconds might feel like 5 or 10 seconds. Conversely, during routine or boring activities, hours might seem to pass in minutes. This is not because objective time speeds up or slows down. Objective time, as measured by clocks and physics, remains constant. Rather, the brain's processing is altered, and this changes the subjective experience of duration. During emergencies, the brain may process more information per unit time, creating more moments of consciousness. This abundance of moments makes the same objective duration feel longer subjectively. Temporal lobe epilepsy can cause distortions of time perception. Some patients with this condition report experiencing the same moment over and over, or experiencing time flowing in reverse, or experiencing multiple different timelines simultaneously. These altered experiences are caused by dysfunctional neural activity, not by actual changes in physical time. All of this suggests that time, the passage of time, the flow from past to future, the distinction between present and absent, is not a feature of the external world. It is a construction of the brain, a product of how the brain integrates and interprets sensory information. The physicist Paul Davies has argued that time is not a universal feature of the cosmos, but rather emerges from the interaction between consciousness and physical reality. From this perspective, time is neither purely subjective, existing only in minds, nor purely objective, existing independently of minds. Rather, it is an interface between mind and matter, the place where consciousness interacts with the physical universe. If this is true, then the answer to "is time actually real?" becomes paradoxical. Time is real in the sense that it structures our experience, guides our behavior, and seems essential to understanding anything. But time is not fundamental in the physical sense. It is emergent, created, constructed by brains observing physical systems. Strip away consciousness and brains, and time might cease to exist. Among physicists and philosophers, there is fundamental disagreement about whether time is actually real. Two major positions have emerged: presentism and eternalism. Presentism is the view that only the present moment is real. The past existed, but it no longer exists. It has passed away. The future does not yet exist. Only the present is real. From this perspective, the flow of time is not an illusion. Time genuinely flows from the past through the present into the future. Each moment comes into being, exists, and then passes away. Presentism aligns with our everyday experience. We feel the present as real and vivid. We remember the past as something that happened but is now gone. We anticipate the future as something not yet real. Our sense of being alive seems to be rooted in being present, in having an experience now. Eternalism is the opposite view. The past and future are just as real as the present. All of time, all moments, all events exist simultaneously in space-time. There is no flow of time, no becoming. The universe is a static, four-dimensional block in which all events are eternally arranged like a landscape, with mountains, valleys, and rivers. The sensation that time flows is an illusion created by consciousness. Eternalism is supported by Einstein's relativity, which treats all moments in time as equally real and accessible. If relativity is correct, and if there is no privileged reference frame, then there is no objective present moment. All times are equivalent from the standpoint of physics. The relativity of simultaneity is particularly troubling for presentism. If different observers disagree about which events are simultaneous, then there is no objective present moment that divides past from future. What is present for one observer is past or future for another. This seems to suggest that presentism is false. The present moment is not an objective feature of reality. Yet some physicists have attempted to defend presentism. They argue that even if relativity is correct, we can preserve a presentist view by accepting that the present is objective but observer dependent. The present is the boundary between what you, at a particular location and with a particular motion, can causally influence in the future and what could have causally influenced you in the past. From this perspective, presentism is true, but the present is relative to an observer. This view is sometimes called the growing block theory. According to this theory, the past is fixed and unchangeable. It is eternally real as a completed fact. The future does not yet exist. It is not real, only potential. The present is where reality is growing, where the future is becoming actual, where possible events are being decided. The growing block theory seems to align with both physics and intuition better than either strict presentism or eternalism. It accepts relativity while preserving a sense that time flows and the future is genuinely open and undecided. Yet eternalism remains dominant among physicists. The mathematical frameworks of modern physics treat space-time as a complete, unchanging block. There is no variable in the equations representing the flow of time or the becoming of the present. The equations describe relationships and constraints among all points in space-time, not a sequential process of time flowing. The physicist Julian Barber has argued for an even more radical view. He suggests that time should be entirely eliminated from the fundamental description of physics. The universe does not change over time. It is simply a static configuration of relationships. What we call time is a human way of organizing these relationships based on entropy and causality. The universe is fundamentally timeless. This view leads to what Barber calls Platonia, a realm of all possible configurations, or nows, of the universe. Each possible now exists eternally in this abstract realm. Consciousness picks out a sequence of these nows based on entropy and causality, creating the illusion of time's flow. But this flow is not a feature of reality. It is a feature of how consciousness interprets and organizes reality. All of these views have serious philosophical and physical difficulties. Presentism struggles to account for relativity and the relativity of simultaneity. Eternalism seems to conflict with our vivid experience of the present and the apparent openness of the future. The growing block theory preserves some intuitions but introduces puzzles about the nature of becoming and the nature of past and future, and the timeless view seems to fly in the face of everything we observe. Change, causality, the arrow from past to future. The resolution may be that all of these views are partially correct. Time may be real at the level of human experience and macroscopic phenomena. Time may be emergent from the structure of space-time and the nature of consciousness, but time may also be absent or radically transformed at the most fundamental level of physics. Different levels of description may require different concepts of time. If eternalism is true, if all moments in time exist simultaneously in a timeless block universe, then a profound question emerges. Do we have free will? In a block universe, the future is already fixed. It is not potential or undecided. It exists right now, along with the past. Your actions in the future are already determined, already laid out in space-time. You will make certain choices, and those choices are already written into the structure of the universe. This does not mean those choices are determined by prior causes in the traditional sense. In classical physics, if the state of the universe at one moment is completely specified, then the state at any future moment is determined by the laws of physics. If the universe is deterministic in this way, then your future actions are determined by the current state and the laws of physics. You are a slave to causality. But even in quantum mechanics, where events are probabilistic and not deterministic, the future is still fixed in a block universe. The quantum wave function describing all possibilities exists at all times. Future events exist with their quantum probabilities fully specified. Even though the outcome is not determined by prior causes, it is random, probabilistic. The outcome is still fixed now. It already exists in the block universe. From this perspective, it seems like free will must be an illusion. Your sense that you are free to choose, that the future is open and undecided, that your choices matter, all of this is illusion. Your future is already written. Your choices are already made. Your experience of deliberation and decision-making is the execution of predetermined computation. Yet some philosophers argue that free will and determinism are compatible, a view called compatibilism. Even in a block universe where the future is fixed, they argue, you can still be said to have free will. Free will, they suggest, does not require that the future be undecided or open. Rather, free will simply requires that your actions flow from your own desires and reasoning, unconstrained by external coercion. When you make a choice, you are implementing your values and preferences through reasoning and deliberation. This process is you making a free choice, even if the outcome is fixed in space-time. Free will, from this perspective, is not about having the power to change the future. It is about the future flowing from your own reasoning and preferences rather than from external constraint. But this seems to avoid the real issue. If the future is already fixed in space-time, already written into the structure of the universe, then in what sense is your current deliberation free? You are merely following a script. Your sense of making a decision is the execution of a predetermined program. How is this freedom? Other philosophers defend presentism or the growing block theory precisely because they want to preserve free will. If the future is not yet real, if only the present is real, then the future is genuinely open. Your choices now are not predetermined because the future does not yet exist to be predetermined. From a presentist perspective, free will is possible because the future is literally not yet real. Your choices will determine what becomes real. There is genuine openness, genuine possibility, genuine freedom. But this creates a new puzzle. If presentism is true, and the future is genuinely open, then how can the past be real and unchangeable? Why is the distinction between past and future so sharp? The solution some presentists offer is that the past exists as a completed fact, while the future exists as open possibility. This asymmetry between past and future is not a feature of objective time, but a feature of causation. The past can cause the present and future, but the future cannot cause the past. This causal asymmetry is what makes the past fixed and the future open. Yet this still leaves the deeper question: what makes causation asymmetric? Why does causation flow from past to future rather than the reverse? The answer seems to be entropy. Causation follows the thermodynamic arrow of time. The low entropy past causes the high entropy future. When the universe is in a state of maximum entropy, heat death, causation ceases to flow. There are no more changes, no more becoming, no more future. From this perspective, free will is possible only because the universe has not yet reached maximum entropy. As long as entropy is increasing, the future is open and possibilities remain. Choices can be made, futures can branch. The universe is still becoming, but this connection between free will and increasing entropy seems to suggest that free will is not fundamental. It is not a feature of consciousness or agency. It is a feature of the universe's initial conditions, the fact that it began in a low entropy state. In a universe that had reached heat death, there would be no free will because there would be no future becoming. This is philosophically troubling. It suggests that free will is not something we possess. It is something that flows from the structure of the universe itself. We are free to the extent that the universe is still evolving, still increasing in entropy, still becoming. We are prisoners of thermodynamics. Yet perhaps this is acceptable. Perhaps free will is indeed connected to the structure of the universe. Perhaps we are free not because we possess some mystical, uncaused capacity to influence the future, but because we are conscious beings embedded in an evolving universe where change and possibility are still present. Throughout this exploration of time, one concept has remained central: causality, cause and effect, an earlier event causing a later event. Yet causality is intimately linked to time itself. Without time, without a direction from past to future, causality cannot exist. Causality is one of the most basic features of human understanding. We naturally think of the world in terms of causes and effects. This caused that. The ball broke the window because you threw it. The disease caused illness. Smoking causes cancer. We organize our understanding of reality around causal relationships. Yet causality is mysterious. What exactly is a causal relationship? What makes one event a cause of another, rather than merely a coincidence or correlation? Philosophers have struggled with this question for centuries. Some, like David Hume, argued that causation is not something we observe directly. We observe sequences of events, but we do not observe the causal connection itself. Causation is a concept we impose on the world, a pattern we recognize in sequences of events. We call A cause of B if B regularly follows A, and if change in A changes B. Others argue that causation is more fundamental. Causation is not merely correlation, it is a genuine transfer of influence from one event to another. A cause produces its effect, literally brings it into being. This notion of causation is closer to our everyday experience and intuition. Yet physics struggles to define causation precisely. The fundamental laws of physics are time-symmetric. They work equally well forward and backward in time. Yet causation is asymmetric. Causes precede effects. How can an asymmetric notion like causation emerge from symmetric laws? The answer, once again, is entropy and the thermodynamic arrow of time. In the physical world, causation follows the direction of increasing entropy. Low entropy states cause high entropy states. The sun's energy, high quality, low entropy, causes useful work to be done. This work increases entropy in the universe overall. Eventually, all the sun's energy is degraded into useless heat, maximum entropy. At the most fundamental level, causation is not a basic feature of reality. Rather, causation is an approximate notion that emerges when we describe macroscopic systems. At the quantum level, before measurement, there is no definite causality. A quantum event does not cause a specific outcome. Rather, all possible outcomes exist in superposition. The act of measurement reveals one outcome, but the measurement does not seem to be caused by prior events. It is probabilistic, random. Yet at the macroscopic level, causation emerges. The initial state of a system, combined with the laws of physics, determines, or probabilistically determines, the future state. This deterministic or probabilistic evolution is what we call causation. Causes precede effects because the low entropy past constrains the high entropy future. Information flows from past to future. Relativity introduced a subtlety to causality. In Einstein's theory, causality is not instantaneous. A cause cannot have effects instantaneously at distant locations. Instead, causation is limited by the speed of light. A cause at one location can only influence events at other locations if those events lie within the future light cone of the cause. If two events are causally independent, one does not lie in the future light cone of the other, then neither can cause the other. This leads to a profound realization. Causality requires time. Causation is only possible because time flows in a particular direction. If time were not divided into past and future, if causation did not follow the thermodynamic arrow of time, then causality could not exist. From this perspective, to ask, is time real, is almost to ask, is causality real? Because time is real only insofar as causality is real. Time is the structure that allows causation to exist. In a block universe where all moments exist simultaneously, causation is still present, in a sense. Causes in the past still influence effects in the future, but this causation is not dynamic or flowing, it is static and fixed. The causal structure is embedded in spacetime like the rails of a train track. Events follow these causal rails inevitably. The causal structure is real, but it is not dynamically producing effects. It is eternally present. This brings us back to the question of free will. If causation is real and we are causal systems, our brains and bodies follow causal laws, then our actions are caused. They are determined by prior causes. genetics, environment, neural states. Where, then, is freedom? Yet perhaps the question is misframed. Perhaps freedom is not the absence of causation, but the presence of self-causation. You are free to the extent that your actions flow from your own reasoning and desires, not from external coercion. Your actions are caused. They flow from your neural states and intentions, but they are caused by you, by your own mind. This is freedom. In this view, time, causality, and freedom are not in conflict. Rather, they are intertwined. Time flows. Causality connects events. Freedom emerges when causation flows through your own conscious reasoning. Time is the arena in which causality and freedom play out. We have explored time from multiple angles: physics, thermodynamics, relativity, quantum mechanics, neuroscience, philosophy. We have considered whether time flows or whether the flow of time is illusion. We have examined whether the present moment is real or whether all moments exist simultaneously in a timeless block. We have investigated how the brain creates the experience of time and how consciousness emerges in an eternal, unchanging space-time. Yet the question, is time actually real, remains fundamentally unresolved. From one perspective, the answer is clearly yes. Time is real. We experience it constantly. We remember the past and anticipate the future. We age, we change, we evolve. The universe evolves. Stars are born and die. Galaxies merge. Entropy increases. Time is deeply woven into the fabric of existence. Yet from another perspective, the answer is clearly no. Time is not fundamental. Physics treats time as just another dimension of space-time, symmetric with the spatial dimensions. The fundamental laws of physics are time-symmetric. Time does not flow at the physical level. It is a static dimension like space. The sensation of time flowing is created by consciousness observing a static, eternal universe. Perhaps the resolution is that time is real, but not in the way we ordinarily think of it. Time is real as structure, as relationship, as pattern. The past is real in the sense that it has concrete effects on the present. The future is real in the sense that it is constrained by the present and the laws of physics. The present is real in the sense that it is where we exist and where we experience causation. But time is not a flowing medium through which events move. Time is not a cosmic river carrying us from birth toward death. Time is the dimension along which causality is structured, along which information flows, along which entropy increases. Time is the arrow that points from low entropy, past, to high entropy, future. And this arrow exists because the universe began in an extremely ordered, low entropy state. The Big Bang created not merely matter and energy, but also an asymmetry between past and future encoded in the initial conditions of the universe. This asymmetry is what gives time its direction, what creates the arrow, what allows causation to flow and consciousness to experience the present. We do not know why the universe began in this low entropy state. This is called the initial conditions problem, and it remains one of the deepest mysteries in physics. Why did the Big Bang produce a universe so ordered, so finely tuned? Why not a universe that emerged in maximum entropy, uniform, and lifeless? Some physicists have proposed that this is just how the universe happens to be. No explanation can be given for the initial conditions. They are brute facts. Others have proposed solutions involving quantum cosmology, the multiverse, or cyclic universes. But none of these solutions are proven or widely accepted. What we can say is that time, the time we experience, the time that structures causality and makes the universe intelligible, flows from the initial conditions of the Big Bang. Time is not fundamental. It is emergent from a deeper, more fundamental reality that may be timeless. Yet this timeless reality, if it exists, remains deeply mysterious. What is it? How does time emerge from timelessness? How does our conscious experience of flowing time arise from a static, unchanging substrate? These questions lie at the frontier of physics and philosophy, not yet fully answered, perhaps not yet fully formulated. What we can conclude is this: time is real in the way that consciousness is real. It is not an illusion in the sense of being false or non-existent. It is real as experience, real as structure, real as the arena in which causality and change occur. Yet time is not fundamental. It is not the basic stuff of which reality is made. It is emergent, created, constructed. We are creatures of time. We live within time. We cannot step outside time to view it from the outside. Yet time is not ultimately what we are. At the deepest level, beneath consciousness and causality and change, reality may be timeless, a static block of space-time in which all events, all moments, all possibilities exist eternally. But this is not our reality. Our reality is the reality of time, of change, of becoming. Our reality is one in which the past and future are different, in which causation flows in a particular direction, in which consciousness emerges and experiences the present moment. The question, is time actually real, may not have a single definitive answer. Time is real from the perspective of beings like us, beings immersed in time, experiencing time as the fundamental structure of existence. Yet time is illusory from the perspective of the fundamental laws of physics, which treat time as static, symmetric, and non-fundamental. This paradox, that time is both real and not real, may be the deepest truth about time's nature. Time is real in human experience and in the emergence of complex structures and consciousness, but time is not real at the most fundamental level of reality. Time is what emerges when consciousness observes and interprets the eternal, static structure of space-time. And perhaps this is enough. Perhaps we do not need to fully understand time to live within time. Perhaps we do not need to resolve the paradoxes to experience the present moment, to remember the past, to anticipate the future. Time is real enough for us. Time is real in the ways that matter most. Yet the mystery remains. Time flows, yet physics says time is static. The present moment is real, yet relativity says all moments are equivalent. We have free will, yet causation is deterministic. These paradoxes are not resolved, they are woven into the fabric of reality. And perhaps this is where the story of time must end. Not with a definitive answer, but with an acknowledgement of profound mystery, a recognition that time is one of the deepest aspects of existence, and that we are only beginning to understand what time really is.